Hello everyone, my name is Onesmus Mulwa Munyao from Kenyatta University, Nairobi, Kenya, and my work focuses on microbial influence on physico-mechanical and microstructural properties of cement mortar. Welcome. Concrete is described as the second most used material on earth after water because of its availability, durability, and low cost of preparation. Whereas concrete is the most preferred construction material, it is subject to degradation during its service life. Most of concrete structural failures have been linked to ingress of aggressive materials such as sulfates and chlorides within the concrete matrix, which have been shown to cause serious durability threat on concrete structures. Recent studies have shown that bacteria are capable of causing significant amounts of damage to concrete, especially in sewage systems. In Kenya, for example, we have had serious structural failures for the last 5 years. Most of these failures have been linked to poor workmanship, inconsistencies in quality of mixing water, and poor engineering designs. Whereas bacterial influence to concrete degradation has been a subject of interest in European countries and in America, very little attention has been given on the contribution of microbes in deteriorating cement structures in Kenyan market. And therefore, this work sought to establish the contribution of bacteria in deteriorating Kenyan-made cements. The mechanism of bacterial biodeterioration of cement follows a series of reactions where in a sewage setup, for example, the sulfur-reducing bacteria produces hydrogen sulfide under anaerobic conditions, and the produced hydrogen sulfide undergoes oxidation by the sulfur-oxidizing bacteria to form biogenic sulfuric acid. The formed biogenic sulfuric acid reacts with the cement portions which are soluble to form gypsum and etrigite as illustrated in this flow diagram. Once the biogenic acid has been formed, it attacks the calcium hydroxide within the concrete matrix to form gypsum, which is an expansive material. Once the formed gypsum reacts with the aluminate portions of the concrete to form etrigite. Now, the reaction mechanisms are shown in those equations, describes how the formed biogenic sulfuric acid attacks the cement and results to formation of secondary materials which are deleterious. Equation 4 and 5 shows the formation of gypsum as a result of the reaction of biogenic acid, the calcium hydroxide, and the resultant gypsum reacting with tricalcium aluminate within the concrete matrix to form etrigite. The formed etrigite is expansive and might result to cracking of concrete structure. The aim of this work focused on the Bacillus intermedius, one of the Bacillus strains of bacteria known to produce sulfuric acid. And the idea was to look at the influence of this bacteria on the microstructural properties of hydrated Kenyan-made OPC mortar and investigate on the compressive strength performance of OPC mortar when made using this Bacillus intermedius. The materials involved in this experiment involved ordinary Portland cement, grade 42.5 conforming to Kenyan standard, and standard sand conforming to EN and ISO. Bacteria spores for this experiment were obtained from German collection of microorganisms and cell culture, whereas the analytical grade reagents were locally purchased to prepare the bacterial culture. The reagents used in this experiment included ammonium sulfide, potassium phosphate, calcium chloride, manganese sulfate, sodium sulfate, magnesium sulfide, and iron 3 chloride. Mortar prisms were prepared in accordance to the Kenyan standard, and water cement ratio of 0.5 was adopted in preparation of both the microbial mortar prisms and the control mortar prism. The control mortar prism was labeled as OPC control, whereas the microbial mortar prism was labeled as OPC TI, TI to mean the Bacillus intermedius. Scanning electron microscopy was adopted to determine the morphology of the hydrated mortar after 28 days of curing, and this was carried out for both the microbial mortar prism and the control mortar prism. Compressive strength was monitored for a period of up to 90 days from the 7th day of curing for both the control mortar and the microbial mortar prisms. The test results indicated uniform distribution of hydration products within the pore system of the control mortar as shown in figure 1, that is SEM image A. OPC control showed uniform distribution of calcium hydroxide plates within the pore system, whereas there was etrigite formation within the control OPC. This was attributed to the initial gypsum added into the cement to improve on the workability and control the setting of the cement. Figure 2 on the other side showed the SEM image for the OPC-TI, that is OPC in Bacillus intermedius, the mortar prism that was prepared using the Bacillus intermedius as the mixed water and cured in the Bacillus intermedius. And as shown, there was a lot of etrigite formed within the pore system. And this was purely attributed to the bacterial activity because from the control mortar prism, there was minimal formation of the etrigite, whereas in this particular one, there was clusters of etrigite within the pore system, an indication that the Bacillus intermedius contributed or participated in formation of etrigites within the pore system. This is has been shown in the literature that Bacillus bacteria, or rather Bacilli bacteria, have the ability to produce biogenic sulfuric acid, and as stated, this acid would react to the cement and result to formation of etrigite as shown in this SEM micrograph. The compressive strength, on the other hand, was monitored for 90 days, from the 70 days to 90 days, and it is clearly shown that the mortar prism prepared with the Bacillus intermedius bacteria showed deterioration of compressive strength, or rather decline in compressive strength from the 28 days up to 90th day. The extreme deterioration was observed on 90th day, where the mortar prism prepared with the Bacillus intermedius bacteria reported low compressive strength as compared to the control mortar prism. This again was linked with the influence of the bacteria into the cement, and it was clearly indicated that this bacteria was affected the mechanical property of the cement, and that is the compressive strength. From this work, we were able to conclude that the Bacillus intermedius indeed resulted to formation of deleterious compounds within the microstructure of the OPC mortar. This bacteria lowers the compressive strength of the OPC mortar as well. I wish to acknowledge my supervisors, Professor Joseph Karanja Thiongo of Kenyatta University, Nairobi, Kenya, and Professor Jackson Wachira Muthengia, University of Embu, Kenya. And of course, African Development Bank, in collaboration with the Ministry of Education, Science and Technology, Kenya, for the PhD scholarship. Thank you.